Good morning everyone, Senan this side, and in this video we are going to solve this LeetCode daily problem, which is most stones removed with same row or column. So before you switch on to a different video, I'll show you two examples I'll show you two dry run of the code basically, or how are we going to approach this. And after doing that, you would be able to write this code on your own. You don't really need my help after that. But let's look at the question. We'll see the examples, test cases, and then I'll show you the code in the end, and then we'll discuss the time and space complexity of that solution and what is a better way to do this question, right? So the given question is, on a 2D plane we place n stones, right, at some integer coordinate points. Each coordinate points may have at most one stone. A stone can be removed if it shares either the same row or the same column as another stone that has not been removed. So you would be given an array of stones of length n, where stones of I, x of I, and y of I represents the location of the ith stone. So what we have to do is return the largest possible number of the stones that we can actually remove. So look at the test cases, and the answer is 5. We'll look at this in my notebook, right? So just see some examples and test cases. So in this case the answer is 3. So technically the size of the array doesn't allow or help us to give you a proper answer in itself. So what we have to do is to understand the fact, first of all, you are not given the size of the matrix, right? You are given 0 0 0 1 1 0 and all the remaining elements, but the maximum value is bounded by 2 and the minimum value is bounded by 0, right? So in this question you are not given the rows and columns. So what you can do is either you could find that, and that is required when you're using a better approach than what I'll be showing you, and I'll just explain in the end what you have to do. Let's understand this problem and look in my notebook first. So the very first thing is, you see, this was the first example and the answer we got was 5, right? This was the answer, and the number of stones we have is 6. Number of stones, basically 6. Now let's look at what the problem is stating. So problem is stating, if there are two stones sharing the same row value or the column value, I can remove one of the stones. So if you see, these two stones are sharing the column value and these two stones are sharing the row value. So what I do is I remove this. Say I remove this stone. So I have removed one stone till now. Now what I see is, for this stone I see it is sharing the row value with this particular stone. So what I could do is I can remove the stone as well. So I'll do that. I remove this. I change the removed stone to 2. Okay, we are good till now. For this, right, I see this stone and this stone are sharing the same column value, so I can remove either of them. So let's remove this one. To do that, I'll use the blue pen and I update the number of removed stones as. Now what the next thing you could do is, you see this, and see this. These two are sharing the row value, so what I can do is just remove this stone and update the counter as. And now what I see is, and these two stones, which are the only stones left in this matrix, these two are sharing the row value, or I mean the column value, so I can remove either of them. So I'll remove this one and I update the counter as 5, and you see we got the answer as 5. But the world is not as simple as it may seem. Now I'll show you a different example in this grid itself. Okay, so here we are back again, and what I will do is remove the stones in a different order. So I could either start here again, or let's start it from this location, just to emphasize the point that the starting point and the way you remove the nodes or the stones actually matter. So I see this, and let's say I remove this first stone, and so this was previous one, right? And current is, so I've removed one stone and I call this as current, just to emphasize that this was the solution in the previous way and this is the current. Now I see these two are sharing the same column value, so I'll remove this one. So I update this current too. Now what I could do is, I see these two are sharing the column value, so I'll remove this bottom one. So I update the counter to 3, and now if you see, these two again are sharing the row value, so let's say I remove this one. So what is so I remove this and my current is 4. Now if you see, this stone is having no more stones which are not removed yet, as well as sharing a row or a column value. So in this there are no more stones apart from this stone itself. So what do I do is, I cannot remove the stone. Similar is the case with this stone. There are no more stones in the same column or the row which are not removed yet. So at max, in the end, we would be remaining with 2 stones in the grid. So since we need to return the maximum, we have to return this, the maximum value. And now why do I say this 5 is the maximum? The reason is because in the last case, right? In the last case, what happened was we were at a case like this. And in the end, if you see, there is exactly a single node or single stone. So when we know it is a single stone, we know that there are no more stones left in the grid. So we cannot actually remove this at any cost. So in the end, we would at least have a single stone in the grid in the worst case, or in the best case, I mean. So in that case, the answer would be 5. That is why I'm saying the answer is 5, because there has exactly 6 stones and I was able to remove the remaining 5 stones. So what I am left with is a single stone, and given a single stone, I cannot do anything better to remove the stone as well, because to remove a stone, we should at least have 2 stones right on the grid. So this is the idea of this problem. And now how do you actually do this? Do you try all possible cases, all possible ways to remove a stone and see how many stones were you able to remove? And that would take a recursive complexity which is exponential, so we don't go that route. So what I do is I'll just re-explain you or re-show you a different way to solve this problem or to understand this. Right now, treat this as a graph problem and these stones as basically some nodes. So two nodes are connected if they share either the same row or the same column, right? So these two are sharing the same row, so they are connected, so these are part of the same group. Now if you see this, these two stones share the same column, so these two are connected, and since these two are connected, these two are connected, this is connected with this somehow, indirectly, directly, doesn't matter. These three stones are connected. Now if you see this similarly, if you see this case, these two stones are connected because they share the same column value, and these two stones are connected because they share the same row value. So this is connected with this is connected with this, and since this stone is connected with both up and left, so these two stones are also indirectly connected. So you have one island here, one island here. But if you observe carefully, we till now we considered only the adjacent element, right? But for this one, this is also connected with this, right? Because it shares the same column value, right? These two stones share the same column value. So what is happening is these two are also connected. Since these two are connected, these two are connected with this, these two are connected with this. So in a way, every node, every stone is connected with every other stone in this case, like a very trivial case. So that means the number of islands is what, or components is what, it's 1, and number of stones is what, 6. So what I do is number of stones minus number of islands is my final solution, if you observe, right? And I'll show you a different test case here. See on the bottom of the screen, there's a different test case as well. And if you see this number of stones is 6, number of islands is 1, and if you subtract this, you 5, and that is your answer, right? So I hope you get the idea. And now we'll do the same thing in this test case as well. You see, first let's just randomly remove that and see what answer we get. So what I'll do is I'll remove this stone because this is shared with the row value is shared among these two stones. I'll remove this column value shared with these two stones, and I cannot do any more. Now I remove this stone because these two are being shared. I can remove this stone as well because these two are being shared, so I remove this. Now I see these two are sharing the row value, so I remove this stone, and what I see is these two are sharing the column value, so I remove either of them, so I remove this. Now for the remaining thing, what you'll see is so these two are sharing a column value, so I remove one of them. So how many did I actually remove? If you count 1 2 3 4 5 6 7, so the answer to this question is 7, or value better than 7. But I would tell you this 7 is the best that you could get. Now if you go by the another route, right, if I remove it in a different order, so what would be happening? Again, we are starting from this, and rather than removing this first, I remove this, and yep, I cannot do anything else. And if I remove this and then I remove this for let's say for example, and in the end let's say I remove this as well. So I was able to remove only 4 stones, but you see this stone is not sharing a row or column with any other stone. This stone is not sharing a row or column. This stone is not sharing a row and column which is not actually removed. It is not sharing a row or column with a stone which has not been removed yet. Similarly for this, no stones has same row or column, same for this, same for this, for this, same for every other, right? So we cannot improve than this. So in this case the answer is 4, but in the last case we got 7 as our answer, right? And that would be the max we could actually get. Now let's actually create all the islands. Basically, how are we going to do this is basically create a sort of a graph like structure, or maybe hypothetical graph. And now let us create the islands. So what I'll do is, if you could see, this is connected with this is connected with this is connected with this. Similarly, this is connected with this goes here, do a jump, this is connected with this. So basically this notation is used basically in electrical engineering just to show that these two lines are not intersecting, but anyways, and these two are connected. So the number of islands is what? Number of islands is equal to 3. Number of stones written above is 10. The answer is number of stones minus islands, which is 10 minus 3, 7, and 7 is our answer. So now we understand this is a graph problem. Basically we need to identify the number of islands in this, and we can easily do with a depth first search. Now let's look at the code. So now if you see, we have this function remove stones, and I create a visited array, and then I get n as the number of stones. So I create the number of islands a counter, I store a counter, and till the time visited is false, what I do is I count, I do a DFS traversal, and whenever I come out of this I increase the value of the number of islands, and in the end we just return n minus count. Now how do we actually do this, right? Now the DFS would take the current index of the stone that we are looking at. We would be taking the remaining stones. So if you see, I've used type def just to rename this whole to VVI, vector of vector int, and this to V of I, because it is easier to write everything. If you understand what is VVI, you're good to go, because the function signature would get very long and it's not that easy to read for me. And so what I do is I get the row and column of this current stone. I mark that stone as visited. I get out the row and column of the stone. What I do, and for the remaining number of stones I see if it is not visited, and it shares. So if not visited, that means the stone is still present on the grid, but at the same time it shares row or a column with this a different node, different stone. So this stone is if it shares a row or column with a different stone, that means it is a part of the same island, so I call a DFS on that node. So through this I would be able to count the number of islands, and yeah, in the end you just return this number of stones minus number of islands and you'd be good to go. So what is the time and space? So the space complexity is big O of n, where n is the number of nodes clearly, but what is the space time complexity? So space is big O of n, and big O of n for the recursion stack space of this DFS, whereas the time complexity is for this for loop is big O of n, and the DFS throughout the journey would go to all the nodes, and to every node we have a linear search of throughout all the elements. So we would have big O of n times big O of n, which is big O of n square for this first search. Although it is good enough for this problem to be accepted, but it's not the most optimal way that you would do this, right? So this is one way. You just call DFS. So DFS would take big O of n square. This for loop will take big O of n. So the net would be big O of n plus big O of n square. That was again big O of n square, and it is not big O of n cube, because this DFS n square is throughout the function call. It's not like for every iteration I'm going for n square. It's like for throughout the execution of this function we would travel basically, and so that is why we are just summing big O of n plus big O of n square, not multiplying them. Space is, as I said, big O of n for this, and for storing, and big O of n for the recursion stack space. You see the code is accepted, but it's somewhere lagging behind, right? For that is you could solve this in a much better time complexity by slightly compromising the space, and may or may not be compromising the space. For that you would be using a disjoint set data structure, right? So you'll basically take the number of rows and the columns in this matrix and treat them as nodes, and whenever you see a stone with a row and a column, what you try to do is take the union of them, disjoint set. So that would definitely improve your time complexity somewhere close to linear time. So all the solutions that you see that are lying in this upper edge are using disjoint set, but since I've not taught disjoint set on this channel, and disjoint set is not very easy for beginners to learn. I thought that DFS would be more clearer to people who want to solve this. At least would get idea that what we have to do. Basically, we need n and the number of islands, and if you are able to figure that out, that is what the question is asking you to. But using a disjoint set is just an optimal way or a better way to approach for this problem. So yeah, that was the video. Hope I was able to explain this to you, and definitely this video is going to, or it is quite long, so thank you for sticking around, and I'll see you in the next video.